Hello everyone. In the last class, we discussed about the characteristics of a digital image, in particular, the sampling and quantization aspects. Then it is followed by how an image is stored. So assuming some B number of bits will be used for storing a pixel value, how much would be the size of the image given B bits are used for storing a pixel value? What would be the range of intensities that we could store? Followed by that, we also discussed about the 3D image and in particular this RGB, hue, saturation, and that magnitude value, HSV. These are the things that we discussed in the previous class. And in this class, what we are going to discuss is we start talking about the enhancements in the spatial domain. So given an image, how could you enhance that image? More specifically, we will be discussing about pixel-based intensity enhancements in a given image. Actually perform these enhancements either in the in the spatial domain or in the frequency domain. As we were discussing in the previous classes, some types of enhancements are convenient, are effective when you do them in the spatial domain, and some in the frequency domain. So we will start looking into the spatial domain enhancements of an image. Okay. Well, again, these enhancements can be further looked at in two different ways. One is an intensity enhancement based on that particular pixel value itself. Another is by performing this enhancement by looking into the intensities over a neighborhood window or a window around that pixel. Okay, of course, this could start from a small window as small as 3 by 3 to the entire image also you might be looking at. And if you want to mathematically represent this enhancements, this is how you could write it. We have already seen, you could see a 2D image as a function of two variables or parameters, x and y, f of x comma y. And this f of xy would give you the intensity of the pixel which is indexed, whose location is indexed by x comma y. Let's say the x could be the row value, y could be the column value, and a pixel there. Now f of x comma y will be giving you the intensity value at this pixel. So when you are doing intensity transformation, at the same x comma y location, g of x comma y would be giving you the new intensity value assigned to that pixel which is present at the location of x comma y. So you have, let's say, intensity x comma y is your new image, your original image, sorry, and the new image be g of x comma y. This intensity at this location you are replacing with some other intensity g of xy. For that you are applying a transformation on it. Okay, hope the way we are mathematically defining the intensity transform is clear. Or any question there? These are some standard intensity transforms that you could think of. On the x-axis, these are, so we have already discussed what could be the range of intensity values. So assume that there are L intensity values. Okay. So then the values could go from 0 to L minus 1. These are the input intensity values. You are going to map each of this intensity value to another intensity value, and this mapping is given by this graph. So on the y-axis, you have output intensity values. Let's say we are calling this as R for input intensity value. The corresponding for a given value of R, the output intensity, you are referring to as S. Let's start with a simple one and then keep on analyzing what does this transform mean and when should we go for a particular type of transform here. Okay, let's start with this simple thing, which is this one, this line. You see how the intensity values which are there from 0 to L minus 1, each of them got mapped. So this mapped to the one in y-axis. So I would like particularly those students who haven't taken medical imaging course, I want them to respond on priority. Good. Any attempt? And what does that mean? What is it doing? Just tell me in words.
The output image would be the same as the input image since it's identity transformation.
That's all. It is not doing anything. It is retaining the same thing. You look at this, you see here, 0 got mapped to 0. Here L minus 1 got to map to L minus 1. This is a straight line joining the both. Okay. So R equal to S equal to R here. It's not doing anything there. Now, can you comment about next simpler one about this negative transform? We are done with identity transform. Now I want you guys to just talk about what does that negative transform mean.
We get output image in which black components turn into white and white into black.
That's all. You are right. So this is like flashback stories told in movies. Suddenly the colors would change, where the brightest, of course, the negative will have, even this comes from the way a negative earlier in your films, the films which used to capture the images, the films that are there in a camera will be there. So the brightest will be the darkest here, and the darkest will be the brightest, exactly the inverse. Sometimes when your objects of interest to be inspected in a given image are in the black region, this might be more convenient for you to visualize things. Okay, only in such things you would be applying it. Otherwise, it is not very common as such. Anyway, identity transform means you are not applying any transform, and negative transform is you are flipping black to white and white to black. So a small L by 4 intensity will go to 3L by 4, and of course the inverse, right? So these 2 points should tell you you are done with this thing. Okay, now I want you guys now to comment about this log transform. What is it doing? Can you shed some light? If you want me to write that log function, that is equivalent to log of 1 plus R, okay, and this should give me S, and I need to again bring it back to the range of 0 to L minus 1 here. So I'll have a constant multiplied with this. This is the transformation. Given an intensity value of R, I would be doing log of 1 plus R multiplied with C, such that this again would come to the range of 0 to 255 if I'm using 8 bits there. Now, maybe before I go there, can anybody shed light on why perhaps I'm using here 1? Why not simple logarithm of R?
Sir, our input intensity starts from 0, but we cannot have log of 0. So we are adding 1.
That's it. Good. That's all. So for that reason, I have log of 1 plus r. I myself have told you why there is c here, right? It is because you want to bring it or scale it to 0 to 255. If whatever you are giving a logarithm of r, assume that I am getting, I don't know, I'm just putting some number like 10. What I would do is, what would be my c then? For maximum value of r, if I am getting log of 1 plus r equal to 10, what should be my c value?
25.5.
Yes, 25.5. Good. That's all. Okay. Now, by looking at the shape of this curve, logarithmic curve, can you tell me what it is doing in terms of scaling those intensities of different regions? Or maybe I'd give you a hint also. Consider the case when your intensities are low in the input image. What is happening to the range of intensities when they are low? What is happening to its range in the output versus some intensities are high? What is happening to its range?
The darker regions become more intense. So we could generally
Yes.
say that we can say that it becomes more bright.
Yeah, maybe I will give you few more keywords here. Look at when you say you consider a patch of intensities here or a band of intensities here with respect to whether that band is increasing or decreasing. When it comes to when this band, you look at these band of intensities in low intensity region versus high intensity region. Now you try to, I know you have some intuition, but based on this you refine your statements.
Smaller range of intensities are getting mapped to larger ranges of intensity
When
when it comes, and in the other case, larger range of intensities values are getting mapped to lower range, like
right, in which
bandwidth.
range? No, your statements are correct. When is smaller range is becoming higher range? Is it in low intensities or in when it comes to high intensities?
When it
High
comes to
input
inverse log or log, sir.
log. This one.
For log, lower intensity values are getting mapped to larger range of higher intensity values.
Right.
And it's inverse in the case of inverse log.
Very good. Very good. Correct. Look at this. Consider, for example, this. Let me draw a line here. Now, please, every one of you, please pay your utmost attention here. This is the range of intensities that are now getting mapped to this range of intensities. I could say something around L by 8 here, half of L by 4. It is almost going to this. I could write it as 2L by 4, 3L by 4 in between, right? So a small range of intensities here are getting mapped to a large range of intensities here. And after that, you look at, for example, till here, let's say, even this whole thing, it simply got mapped to this region here. This region, this whole region got mapped to simply this region, the rest. On the contrary, look at this inverse log. And let me now draw, let's say, from 3L by 4 to L minus 1. What is happening here? Let's say this 3L by 4 is roughly mapping to L by 4. And L minus 1 is, of course, L minus 1. So what is this length here? Length of this is roughly L by 4, is it not? This is 3L by 4, that is 4L by 4 roughly. Forget about minus 1. So L by 4 minus 1 if you want to have it precisely, but L by 4. This is how much? 3L by 4. In other words, the contrast of those pixels which are at the high intensity level or high intensity range has been enhanced in case of an inverse log, and in case of a log transformation, the contrast of those pixels that are lying in the low intensity range are getting enhanced. Is everybody able to see this picture? I mean, you can see this picture, interpretation from this picture. Any questions? So when do you use log transform then? What is the symptom that you could look in an image that tells you that you should go for a log transform or an inverse log transform?
There's no contrast.
No contrast in which region?
Like it's only dark for in case of log. When the image is completely dark, in order to enhance the contrast, we use log transform.
And what about inverse log?
If it's too bright, exposure is too much, then
Right.
we can use
Correct.
inverse log.
Correct. Very good. See, a small range in the, let us look at the dark one here. Okay. So a small range of intensities, that means low intensities got mapped to a bigger range there. So when most of the content of your image is within a small intensity range, you can still have high intensity pixels, but their content is, number of pixels in that is less. Most of the content is in low image, low intensity region, you would go for log transform. In exactly the opposite case, you would go for inverse log transform. Well, this doesn't give you too much of flexibility in playing with this shape of this curve. Okay, so I'll just jump so that for the sake of continuation, this is another way you could do, where my function is something like this. Let's say S is equal to R to the power of gamma. S is equal to R to the power of gamma. Okay, and of course, again, I want to bring the scaling to 0 to L minus 1. For that purpose, I put C here. That is the normalizing factor now. And unlike the earlier function, how did we write C equal to S equal to C into log of 1 plus R. R is your input intensity. You don't have a control over that. C is something, a constant to normalize it to your range, let's say 8-bit, 0 to 255 to normalize that you are using it. So you don't really have a control over the shape of the curve. On the other hand, if I use a transform like this, which is a normalizing factor to bring it to 0 to 255, but here R to the power of gamma, where I can play with this gamma. Suppose if I put gamma equal to 1, what would happen? S equal to C times R. R is varying from 0 to 255. So my C also I would then have to fix it to 1. So in that case, S equal to R, this is the one I would get. Gamma equal to 1 will be an identity transform. Now, there are two positive. Gamma is a positive non-negative value. Now, R, in fact, I could say is a positive value. R is less than, so I would use something in between 0 to 1. Then you would see as I reduce the value of R, it will be moving in this direction as I am reducing the value of R. And more than 1, if I am increasing, this will go on in this direction. These curves will be going in this direction when I am increasing the value from R equal to gamma equal to 1. It's not R. R is the input intensity. Here also, this is not R, this is gamma. This is also gamma. So what can you see here? Which patch here should have a maximum mapping and to what range it can map? You are able to play with this. This is called as, you have a power here, so they call it as a power law, or this also is referred to as gamma transformation. This is standardly even in your monitors, screens that you use, and if you, the conventional ones, or even now could be somewhere in a different way, you will have a control over this. Or if not, you are given the control, it is fixed to some value. The same thing happens even to your TV screens. By playing with it, you could see those intensities getting mapped differently. This is possible. And this is one important, simple, effective transformation. Is this clear? Or any questions on this? This is a very, very important transformation. Any questions on this? Then look at this image. This is the image, MRI image of the human spine. Okay. And you would like to notice here if there are any fractures. This is for a, so this is the one you obtained as a result of your, let's say, your MRI scanning. And that's, let's say, the sagittal view of that. Now, you could notice here well that this region is pretty dark and you could hardly see anything. So should you go for gamma less than 1 or gamma greater than 1?
Less than 1.
Right. It is the reason being, when your gamma is less than 1, your graph would something like this. So a smaller range of your intensities, you are mapping them to a larger range, so you could see them better. The same thing you could notice here. For example, they used here gamma equal to 0.6, 0.4, and 0.3 here. Okay. So more and more it's becoming brighter. So if you further increase, so lower value would have been something like this. So higher values are, the saturation would come much earlier. So even more values get mapped to a brighter range. Is everybody able to see the impact of playing with the gamma, and whether gamma should be greater than 1 or less than 1, and why? These three have to be very clear. Then I will go to this image now. See, this has been taken in a bright light, day bright light, okay, daylight condition, very high light condition. Or it could have been a reason of high exposure time of a camera as well. Now you could hardly make a distinction of things here. So those which are on the bright side, you want to map them to a, you want to bring a high contrast there, high distinction there. If you see linearly from 0 to 255, that mapping is what you are changing now. So what is the way you want on the brighter side, right? So maybe rather than drawing it, I'll show you here itself. Look at something like this, as we were discussing. On the brighter side, this range, you could see, got mapped to this range now. Hope that is clear. So small, even a small one here, from here to here, this intensity would now get mapped to, this would be the gap here. If this gap, now in terms of intensities, this much gap would be there for the next one. Right. There are other ways of transforms that you could think of also. This is one way. Well, you see here, it's a low contrast image. You could tell that by looking at the image. This is what you should practice. Very dark regions are not there, very bright regions are not there. So that intensity, if you look at it, the intensities are somewhere in between the dark and the bright over a particular region. So what you could do in fact here is you may give one kind of mapping to higher and lower values, and in between you could map them to a bigger range. So this is something, if you are using any of these tools, they will help you do this, where you could fix number of control points there, and in between control points you can play with the slope of this transformation. Is that, and that could eventually give you this type of image. Okay, thresholding part anyway, I will come to that a little later. This is referred to as a piecewise linear transform, because unlike the gamma, where it is kind of a polynomial one you are applying there, this is a linear transformation that's happening between, let's say here, if you look at it, so the small range is getting mapped to a large range with some particular slope, and the slope has changed here. Again, it is piecewise linear. You could consider how many pieces you want it, but still it's not completely linear over the entire range, but it is piecewise linear transformation that you are doing. And I think I left a few here in the beginning, so let me come back there and see if something important has been missed. Yeah, this is another kind of transformation which you could refer to also as thresholding. This is one type of thresholding. Of course, there are other ways you could threshold an image, where you, for example, know that your object of interest in the image area that is within the range of this k to L minus 1. And let's say your background is from 0 to k. This is your background and this is your object. Let's assume that. Then what you can do is you make this entire thing 0 and you just show this one here. For that, where you have an object. Well, this is under specific situations, you'd be applying something like this. Let's say you want to create a mask of your object. By mask means you are not really interested in looking at the variations within your object, but just to show the region of your object that is of your interest. So the whole thing, let's say, you could represent it with 0, and this you could represent with simply 255. And of course, you could make it to 1 also, nothing wrong with that. So this is one kind of intensity. Sorry, transform. Okay, S equal to C times log of 1 plus R. This is what, with this logarithmic transform, the Einstein would become, like shown on the right hand side. Maybe this example is not so appealing to you, but I'm sure this example will be appealing to you. I'm sure in your DSP course, you would have plotted the magnitude spectrums. And there will be some very high values when you are trying to plot this magnitude spectrum, the Fourier domain for a given image. There are some very high values that would dominate to that extent that you cannot see the contributions of other frequencies, because the different distinction between 0 and that high is so high. In between, you can't really see it despite they being present. But if you are applying a logarithmic transformation, you could see here the small range are also getting mapped, and there is a level of saturation that is brought at the high end. With that, you could visualize it better. Then only you would realize whether there are harmonics present or not. Okay, that way, this is one such transformation. Of course, now you could think of other things also. This gamma transformation with gamma less than 1 also you could use. But in many cases, this particularly when this is sufficient for you, okay, to visualize things, then you would go for a logarithmic transform on top of your DFT results while showing you the magnitude spectrum. We are done. I think this is how this, so what we discussed so far are point-based transformations. That is where I will stop that. And now I will switch on to some other way of looking at an image and getting a progress report of this image, and then based on that applying transformations. What could be considered as a progress report? By progress report, what does a progress report convey? It conveys your overall performance in a very a summary of that. So what can be considered, I would say, as a progress report for an image is histogram. I'm sure by this time many of you would know what a histogram is. I would like some of you to phrase what an histogram is for a given image. How do you draw? I give you an image. How can you draw the histogram of that image?
Every pixel value.
A intensity value of each pixel, right?
Yeah.
Correct. So let me slightly also modify that. It gives the count of number of pixels that are having a particular intensity value. I guess that is what you wanted to convey, correct?
Yes, sir.
Right. So on my x-axis, I have intensities. And these values could be, for example, 0 to L minus 1. And then let's say I have an image of, for sake of simplicity, 100 by 100 size. That means I have 10,000 pixels, right? I'm going to visualize the summary of intensities of these 10,000 pixels. Assume that I'm using here 8 bits to store this. So this L minus 1 is now 255. So instead of the summary of intensities of 10,000 pixels is represented by a histogram that is containing 250 distinct values, where it could tell me, for example, here, this I have, let's say, out of those 10,000, 1,000 pixels are having 0, then 1 is having, say, 200 or 500. Okay, so this way I could have this, its value on y-axis is telling me the number of pixels that have that particular intensity. So it gives me kind of a progress report of number of pixels in that image having a particular intensity values, or in other words, it gives me the intensity distribution of that image. And should I always have 0 to 255, or do you think in what way can I modify the x-axis? Because typically I might not care about such a fine looking at of intensities. I'm okay with some baskets rather than having 255 distinct values there. So what could I do there?
Bins.
into classes.
Right. So what I could in fact do is, instead of having 255, I could have, let's say, something like 25 or 26, where 0 to 9 is my bin 1, 10 to 11, 10 to what should be then 19, my bin 2, right? and so on and so forth. Maybe 250 to 259 will become which bin? Bin number? What would be
26.
that bin?
26.
26. Okay, 25 or 26, whatever it is. Okay, so this is what I can do. And it is still telling me the distribution when I have that bin. So this bin size I could vary with, and I should be able to get a good representation of that image by just looking at here, in this case, 25 or 26 values. Now, what you should get a good hold on is, if you look at the image, you should be able to visualize what would be perhaps its histogram. How does it look like? How the intensities are distributed here in this image. That picture you should start practicing to get, and also the contrary. By looking at a histogram, of course, you can never say what is the content of that image. That is beyond the scope, because you do not know the spatial information. So the same histogram you could get with multiple images, even by jumbling the pixel locations. Okay, the intensities, you could get the same histogram. That, of course, you won't be able to assess by looking at a histogram, but at least how that contrast of that image, that just by looking at histogram, you should be able to make a visualization or an assessment of the image in terms of its intensity distributions. Let us suppose I give you this histogram. What can you say about the image, about its contrast and intensity distributions? What can you say?
Very bright image, no
Very
contrast.
bright image. What about the contrast?
Very low.
Very low, right? So this dark part, there are no pixels with these intensities. You do have the highest intensity here around 255. If you consider it L-1 as 255, it is there, but it is not having a very good contrast. When do you say a very good contrast? The distinction is pretty high. So that means you have more number of intensities available there. So let's see the image. Can you see that now? And hope you are able to correlate with this explanation. Now look at this image, and what can you say? First of all, tell about the contrast of this image versus the image represented by this histogram. Is it more or less? What would you say? Any comments on, compared to the previous one? What would you make? What comments can you make about the image that has this particular histogram?
Better contrast compared to the previous one.
Not really. See here, contrast is, as I said, the intensity distributions are this much. That's what I would say, the contrast. Contrast wise, this is limited. So I would say exactly the opposite. Low contrast image. What more can you say about the brightness of the image? Neither bright nor dark. Somewhere in between, it is lying down. That is the image. Okay. So then this one, what would you say now? What about the contrast? And what about intensity
Very
distribution? Right. So if you look at that image, this is the image for this. And you could see all of them put together here. Maybe I have missed this while I was showing. This is histogram of a dark image, histogram of a light image, histogram of a low contrast image. You could see the distribution is here, relatively bit more here, relatively more here. This is having a high contrast, the distributions are more, and a balanced image. Now, a follow-up question to you is, if I give you this histogram can you think of any linear transformation that would increase the contrast of the image?
Contrast stretching.
Right. So what does that mean now? What is that you would like to do here?
So we can use the log transformation on the first image.
Yes.
It will stretch the.
Right. Good that you made, one of you have made an attempt. I'm saying a linear one. Okay. How we do it, we will work out a little later. But let's say this is somewhere around 100. This is somewhere around 255. What is it that you would like this to be do? Just tell empirically in terms of numbers how you want this histogram to behave. You first tell me that.
So then we'll map 100 to 0
Very good.
and so on and so forth, so that we can stretch it to the left where there is
Right.
no intensity.
Correct. Very good. So what I would like to do here is, that's all. If you express it, things would move faster also. This 100 I want to map it to 0. The maximum one I want to map it to 255. Maybe even a better case is this. This is what I would tell you. This is, let's say, 100. This is 150. This 100 I want to go it to 0. This 150 I want it to go to 255. And then linearly place the rest of the bins in between. Okay. Now you tell me the mathematical form where this is possible. A simple normalization would help you doing this. Okay. So let me call this value as f, where f can have any of these values. Again, I'm here assuming it's just a simple bins there. Okay, I'll just finish it off and then wrap it up. So please bear, otherwise we are in between something. So I will just finish it off and then leave you. So how do you bring, so let me call this as f min and f max here. Okay, then this value let us call for right now as 0 and this as L minus 1. Now, how do you normalize this such that your f min will become 0 and your f max will become L minus 1? Once you do these two, the rest will follow if you are doing writing a linear equation there. So let my new value be called as G. Okay, I have given you all the required variables. There is f min. Here this value is f min. This value is f max. Now my f min should go to 0. My f max should go to L minus 1. Okay, that's all. Now you tell me, how do you write the new value? I call it as G. Any of these values on x-axis, I call right now them as f. F should go to Z. Tell me the linear transformation or normalization that helps me doing this. Okay, you think about it for the next class and tell me then. Right? You make a note of this question and come with the answer in the next class. Right?